Okay, so here we have a case of steroids. So the company has developed a drug test to detect steroid use by athletes. The test is accurate 95% of the time when an athlete has taken steroids. It's 97% accurate when an athlete hasn't taken steroids. So let's suppose the drug test will be used in a population of athletes in which 10% have actually taken steroids. So let's choose an athlete at random and administer the drug test. Okay, so we're gonna make a tree diagram that's gonna show the sample space of this chance process. So the sample basically it's gonna show like all the possibilities. Then we're gonna figure out the probability that a randomly selected athlete tests positive, and then we're gonna figure out what would be the probability that they actually use steroids given that they tested positive. So the good thing about this is that if you make a thorough and clear tree diagram, you can easily answer parts B and C. So let's go ahead and break down how we can make a tree diagram. So what I like to always do is abbreviate the events with like a symbol, like one letter, just to make it easier to read. So what could happen is that you could have that an athlete just taking steroids. So let's have S be steroid. They use steroid use, and let's just have N be like they didn't take steroids. And then the other thing is that they could test positive when they take a drug test, or they can test negative when they take a drug test. So let's put positive. And let's say test negative. I don't know. I guess we'll put N. They will use N to test. Okay, so when we make a tree diagram, you want to first break the tree into the two events that would happen first, that would have to occur first, or that would actually make sense, I guess, when you're doing calculations of probability. So what we would first do is we have that we can go onto two roads. So we start here and we can either go here or here. So it's either that the athlete could be on steroids, so they're a steroid user, or that they're not a steroid user. That's what could happen first. Now, let's say if they are a steroid user. So from there, they then take a drug test, and either they can test positive or they can test negative. The same idea if they're not a steroid user. They could either take a test and test positive, or they can take a test and test negative. So this first path here basically represents the probability that the athlete takes steroids and tests positive. So the probability of S and P. This path be that they took steroids and test negative. The probability of S and N. We got this pathway, probability that they didn't take steroid and they test positive, so the probability of N and P. And the fourth possibility is that they are not a steroid user and they test negative, so the probability of N and N. Let's basically look for what the values of these four probabilities are. Now let's start from the beginning. We have two possibilities. They use steroids or they don't. Now, in the problem, it tells us that let's see. It says that there's 10% of the athletes that have taken steroids. The 10% that have taken steroids are going to put 0.1 over here, 0.10. If 10% of them took steroids, that means the remaining 90% or 0.9 of them didn't take steroids, because these two have to add up to 1. Either it took steroids or they didn't. Now let's look at these next two roads. So it says the test is accurate 95% of the time when the athlete has taken steroids. So we're talking about the steroid user. So we're talking about, going on this pathway and being this or this. So for it to be accurate, they would have to test positive because they're a steroid user. So if it says it's 95% accurate or accurate 95% of the time when you take steroids, it means 0.95 would go here. 95% of the time it's accurate. That means 5% it isn't accurate, so we would 0.05 here. Because again, these two have to add up to 1. Now let's look over here. For the non-steroid users, it says it's 97% accurate when they haven't taken steroids. So if they're a non-steroid user, for it to be accurate, it means that they would test negative for steroids. So that means the 0.97 would go here. That would be an accurate result. And that means there's 3% left over, and 0.03 would be here. So now we have, all those corresponding probabilities labeled. Now these are very easy to find. All you have to do for each one of them is multiply the rows across. Multiply 0.1 by 0.95 to get the probability of taking steroids and testing positive, and get 0.1, 0.95. Here you just multiply 0.1 times 0.05. Here you would go 0.9 times 0.03. And this last one, 0.9 times 0.97. So you crank those out. Calculator technology, 0.95 here. 0.05 here. 0.027 here. And 0.87. And again, to make sure you did all these accurately, you add these all up, and they should add up to 1, because this is all of the possible things that can happen. They do add up to 1 when you add them. So that's a probability tree. I usually like to take the time and label every single part because it's going to make the rest of the problem a lot easier. Now let's look at part B. So what's the probability that the randomly selected athlete tests positive? So part B, trying to figure out what the probability is that they test positive, probability of P. Now, there's 2 possible ways that this can happen. They can either be a steroid user and test positive, or be a non-steroid user and test positive. So all you have to do is add these 2 probabilities up. Because both those together make the total possible ways you can test positive. So since we already did all these values, we just have to add the 0.095 to the 0.027. And you get 0.112. Or sorry, 0.122. All right, now part C. Suppose that the chosen athlete tests positive. What's the probability that he or she actually used steroids? So on part C, we're trying to figure out the probability of them using steroids. The probability of S, but we have a condition. So we said probability of S given, that's what this vertical line means, probability of S given that they test positive. So the probability of them using steroids given P, the probability of S given P. Now, as long as you know how to translate your formula on your formula sheet, what you get, this is actually really easy because we did the full probability tree. So if you look at your formula sheet, it's gonna have this formula that reads. I'm gonna put it over here. It's usually in terms of A and B. It usually says the probability of A. That's not good. say the probability of A given B is equal to the probability of A and B over the probability of B. Get a formula sheet with all with some of the formulas on every test and on your AP exam. So you're gonna want to refer to this one in case you get stumped and can't remember off the top of your head. And it's really just like matching. So like instead of the A, we have an S. Instead of the B, we have the P. So what we do is the probability of S given P will be equal to the probability of S and P, probability of S and P, over the probability of B, instead of B, we put P, over the probability of P. The probability of S and P over the probability of P. And again, since we took the time to make a thorough tree diagram, we already have these. Probability of S and P is right here. And that's 0.095. We go 0.095 over the probability of P, which we just figured out. Part B, found the probability of P to be 0.122. So all you simply have to do is divide those, and you'll get your answer. That'll be about 0.7786. There you go. That's all there is to it.